Some more. Today we're going to talk about Newton's second law. We're going to start with a concept development page, and so I'm going to move my face so that you can see the page a little bit better. I do apologize, it's not the greatest quality, but hopefully you can see it well enough. And I think it really will help us to figure out Newton's second law. Okay, so first of all, we need to think about first law. So 1a says Newton's first law of motion describes motion that can occur under what specific conditions? Well, we know that Newton's first law talks about objects at rest or objects in constant motion, right? Constant velocity. So the condition that has to occur is that there are no unbalanced forces. All right. So part B, it therefore fails to describe motion that occurs when there are unbalanced forces acting. And of course, we know that that means if unbalanced forces are acting, accelerations will occur or changes. Okay? So Isaac Newton wrote the second law here. It's kind of complex, but we're going to break it down and figure it out. So first of all, it's just confirming what we just said. When a body is acted on by unbalanced forces, it will accelerate. Okay? And then it tells us that the acceleration is directly proportional to the net force acting and inversely proportional to the mass of the body. Okay, so first of all, when we talk about net force, we're talking about the sum of all forces acting. You saw in Ms. Bailey's video, or we've seen in class, that net force is symbolized with a capital F and a little subnet. Okay, and it's just a sum total. And so next, that allows us to kind of write ourselves an equation. So this law says that acceleration is equal to, or is directly proportional to, the net force, and inversely proportional to the mass. So think back to the beginning of the class. We talked about direct proportionalities. We see the same things happen. So if the net force goes up, then the acceleration will also go up. If the net force goes down, acceleration will also go down. Okay, so that's a direct proportionality. In inverse proportionality, we see when one variable is on top of the dividing line and one is below, so like the acceleration and the mass, and we see opposite things happen in that case. So that means that if the mass goes up, the acceleration will go down, and vice versa. If the mass goes down, the acceleration will go up. Okay, so you actually don't need to memorize the wording to the law because you can get the wording from the equation. And we're going to apply it here so you can see some examples. So we've got Katie and Kelly in the grocery store. They're doing a little race. Katie and Kelly are twins, so we are going to assume that because they're twins, they have equal amounts of strength. So we see Katie's cart is loaded down, lots of mass. Okay. We're going to write an equation for this. All right, so first we've got Katie. We said that they both had the same force. Okay. So equal forces, equal muscles. All right. And then we see that Katie has lots of mass, really big mass, and Kelly has just a small mass, nothing basically in the cart. Okay, so we're gonna turn that into equations, and we remember from up here that if the mass is big, then the acceleration is little, because they do opposite things. And if the mass is little, the acceleration is big. Okay, and again, that's just an inverse relationship. So we can see that Kelly wins the race because she's just got less mass. Okay. Part B, Kelly and Kevin are racing now. Now, Kelly is older than Kevin, so we're going to assume that she's stronger than he is. Okay, so we'll set up similar equations here. So we've got Kelly and we've got Kevin. And we're saying that Kelly is stronger, so she has a bigger F net, and he has a little F net. Okay, they both have empty carts. So that means that the masses are the same for both. Okay, and now we're going to get an acceleration. So for the top, the F net and the A are directly related, and so they do the same thing. So when I have a big F net, I have a big A. When I have a little F net, I have a little A. And again, that's just that direct relationship idea. And so in wording, we can say that Kelly pushes with more force, therefore she accelerates more. Intuitively, you know this. You know if you push harder, you're going to speed up more, right? You also know if you have more mass, if the object is heavier, you can't accelerate with the same rate. Okay. Okay, so our third example, we see that Katie has her loaded down cart. We see that Kevin has developed the ability to fly now, and we want to figure out why did they tie. Okay, so let's do what we've done, and we're going to draw some equations to figure this out. So we've got Katie, we've got Kevin. So we said that Katie was stronger, so she has a big F net, and Kevin has a little F net. He's not as strong. Then we see that Katie has a loaded down cart, so she has a big mass. And we see that Kevin has an empty cart, and so we have a little mass. And now when we solve for those, we see that the ratio changed in the same way. So they have the same acceleration because a big F net divided by a big mass will be the same as a small F net divided by a small mass. Okay? So Kevin is not as strong, but he doesn't have as much to push. Kelly is stronger, but she has more to push, and so they equal out and they tie in the race. Okay? So that brings us to number 5. Galileo was famous for figuring out that all things accelerate at the same rate on the Earth, that heavy and light things fall at the same rate. And so we can explain that with this. It's just like Katie and Kevin. If you're thinking of the F net as being gravity for an object falling, a heavy object has a big weight, right? Okay, so big F net, or FG, actually, let's change that to FG. Big FG comes from a big mass, okay, and that will equal some acceleration. And then a small mass will result in a small weight. But just like Katie and Kevin, the ratios are the same, and so they both have an A of 9.8 meters per second squared because of that equal ratio. Okay, so that's how we can explain that. All right, so Newton's second law is often written as F net equals ma instead of the way we've been writing it. If we want to identify the units, we're going to do newtons for net force, we're going to do kilograms for mass, and we're going to do meters per second squared for acceleration. Okay, just like we've been doing. So we've got a few that we can practice here. So 7a, what net force is needed to cause a 3 kilogram body to accelerate at 4 meters per second squared? So kilograms is a mass, right? Meters per second squared is an acceleration. And we're looking for the force. So F net equals ma. We're just going to multiply them. We have 3 kilograms times 4 meters per second squared. And that gives us 12 newtons of force. Okay, 7b, what is the acceleration of an 8 kilogram mass? So we've got 8 kg for m, acted on by a 24 newton net force. Okay, so F net is 24 newtons, and we're looking for acceleration this time. So if we're using our kind of standard equation, we've got 24 newtons equals 8 kilograms times an unknown a. So we're going to divide by 8 on both sides to get it off of the right and get a by itself, and we get an a of 3 meters per second squared. And then last but not least, we have c, what is the mass of a body that undergoes an acceleration of 5 meters per second squared, so that's our a. When acted on by a 35 newton force, so F net is 35 newtons, and we want to know the mass. Okay, so we have our same equation. F net equals ma, our second law equation. We have 35 newtons for F net. We have an unknown mass, and then we have 5 meters per second squared for acceleration. We're going to divide both sides by 5 to get the 5 off of the right side and get mass by itself, and we see that mass is 7 kilograms. Okay, so that's our concept development. The slide in the notes is just kind of going over all of that same stuff. So again, first law talks about when forces are balanced and the object is in equilibrium. So when forces are unbalanced, the object is not in equilibrium and it will accelerate. We know that forces cause accelerations, right? And we also know that inertia resists accelerations. Inertia is a resistance to change. And so again, that gives us that equation. We know that we have a direct relationship between the net force and the acceleration, and we have an inverse relationship between the mass or the inertia and the acceleration. Okay? And that's that law that we talked about. So again, don't spend your time memorizing the law. Just remember that this equation is Newton's second law because you can pull all of that wording from the equation.